Let's move on to what we're actually here for today. How about that? Okay, so we're on Chapter 3, which the goal today is understanding power and power supplies. I already said they should be taking notes. We've already done our self-assessment. The chapters over electricity and power supplies. This is our first real hardware section. That's about parts. And the power supply is an integral part. It's also the easiest part to swap in a computer in general. Second easiest part. One of the easiest parts to swap in a power supply, in a computer, but it's the most prevalent to fail in a computer as well. So the first thing we want to understand today is PC form factors. Okay. So we've talked about that word. That word has come out before. What a form factor is. Okay. So when we say form factor, it describes the size, shape, and general makeup of a hardware component. Okay. So the form factor of a video card, this is a PCI video card that I'm holding, that's the form factor. That's the kind of slot that it fits in, whereas this one, if I had a regular, this is a PCI Express, and I don't have a regular PCI one in my little stack here. There's different form factors for different kinds of hardware components. Okay. Now, the thing that drives our PC in general is the form factor of the motherboard. Okay? So when we've gone and picked out our motherboard, then we have to make everything else sync up with that. Now we could start with any component and say, okay, that's got to match that and that's got to match that. But generally, the motherboard drives the decision. We don't go and say, I want to buy this power supply for my computer, therefore I will make a computer that fits this power supply. Because it's an inconsequential part of the PC, meaning that if I buy a really big power supply, a really cool power supply, it does not make the PC run faster. Either the power supply works and the PC runs, the power supply does not work and the PC does not run. Okay? So we usually start with the motherboard, which is the first real presentation you're going to do, because then the motherboard drives all the other things. But form factors, the motherboard, the power supply, and the case are the first three things that have to match to make a good computer. Okay? If I buy a motherboard of one form factor and a case of another form factor, and the holes don't line up, I can't just drill through the motherboard and screw into the case. All the holes have to line up so they screw together. All the things in the back have to line up so they stick out the back of the case. And the power supply has to be able to plug into it so that it gets the kind of power that it needs. Okay? So form factor describes the size, shape, general makeup of hardware component, and those things all have to match for it to all plug in together. It's like mixing Legos and Duplos. You can't do it. They're both building blocks, but if the building blocks don't have the same holes and they're plugging together, you just can't play with them. Okay? They can fight against each other. You can have a Lego guy against a Duplo guy. Okay, so, and those decisions determine what your system is going to be able to do. Okay? Matching form factors assures that, and I already said this, the motherboard fits the case, and that means the holes line up, and I've got a little picture of what I'm talking about, but there's a specific spec for certain form factors that say the screw holes will be here, 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 for all ATX cases, or all BTX cases, or all AT cases, or all LTX cases. Whatever case that is, if you get the right form factor, the motherboard will fit the case. The power supply has to provide the correct voltage and has to have the right in connectors to connect up to the motherboard that you're buying. So those things have to work out. I already said this, holes in the motherboard have to align, holes in the case and the motherboard, those things have to align. And then, for some form factors, there's very specific wires that connect up to the front panel connectors and stuff, and those things have to go together as well. Some of them are proprietary, so that you don't have a lot of choices. Dell uses a lot of proprietary parts, proprietary meaning it's owned and controlled by Dell, so you have to buy the Dell thingy in order for it to work. Okay. Here are some common form factors, but this is the form factor we're going to be dealing with the entire time in this class. Okay? We're going to be talking about the ATX form factor. Everything you buy, every part you select, has to be an ATX form factor part. Okay? Every single year, someone chooses one of the other ones and has to redo a part of their presentation. Let this be the year that doesn't happen. Okay? That really stinks if I give you 2 weeks to work on a presentation and the first thing that we say when Lane goes up there and says, I selected this motherboard as my home motherboard because, and Brooke goes, that's an LTX motherboard. Oh, okay, and we skip. And now Lane has to come back in 2 days and represent. That stinks. So don't let that happen to you, okay? So ATX is the most common form factor around. The second most common is BTX, which is like ATX but reversed. And I will tell you that here at National Trail, the majority of our computers are BTX because for some reason Dell likes BTX as part of their proprietary thing, okay? In all ways, BTX is almost exactly the same as ATX, except for it's flipped over and reversed. In other words, if this was a BTX motherboard, it'd be hanging from the ceiling, okay? It's like a mirror image. BTX is like a mirror image of ATX in almost every respect, which means most things, except for the case, will go from one to another. If you buy something for ATX, it'll work for BTX, and vice versa, except for the case itself, because the holes don't line up because it's on the wrong side. Okay? So when I look at the back of this case, if it's BTX, it'll be on one side, and if it's ATX, it'll be on the other side. When I say it's a mirror image, okay? And then there are some other very proprietary ones, like this one. This is a PC. It's in no way, shape, or form an ATX. It's very proprietary. It's very specific for this case. You're not going to go out and find another case and put this motherboard that comes inside that PC in it without a lot of work and maybe a lot of finagling. Get that to work. So, the ATX form factor, since that's the one we're going to talk about, I'm not going to give you a lot of background on any of the other ones. I'll let you write some of that down for a second. We'll be right back. I have to go to Eaton to get lunch today so that I can change clothes to be twins today intentionally. Okay, so it's the most common open, non-proprietary, meaning anybody can make it. Okay, anybody can make this one. Developed by Intel in 1995. This measurement is for a standard ATX. You're going to see when I show you the diagram. There's lots of other measurements than that. The CPU and the memory are set up in a specific order on an ATX motherboard to avoid interference with each other. The power supply and motherboard use a single power connector called the P1 connector. And that's old. Actually, we have two connectors in the front, so I should switch that. They have a single big power connector, but all of them have a second P4 power connector. This is a good motherboard, and I don't want to mess with it, but I can hold it up. Anyway, so what does that mean? Here's the P1 connector. It has a big P1 connector that all ATX motherboards run by. But all new ATX motherboards also have a secondary power connector that is there for the CPU because the CPUs require so much more power than they used to. Okay, if you have this one plugged in but you don't have this one, it will never boot. Okay, it has to have both power connectors, and this one can come in various sizes. You can have 4 pins on it, or you can have as many as 8 pins on it, depending on which connector plug it uses. So that's kind of a misnomer. I need to fix that on that. Okay. And all the time in an ATX, the power supply blows air out of the case. And that's an important thing to understand as we talk about power supplies, because one of the easiest ways to see if your power supply is the issue with it failing is to do this. If I put my hand on the back of a PC and don't feel air coming out the back, it generally means the power supply is my issue and something is failing. Now this power supply right here is not a huge volume power supply. You can barely feel the air coming out the back of this one. In fact, the only way to really feel the air coming out of the back of this one is to hold something like a piece of paper up and see if the piece of paper, as you put it on the back, kind of pushes away from the power supply. That's how gently the air flows through that power supply. But most of these power supplies, like this one, has a nice big fan and it's blowing air out the back of the case. Okay? The reason that's important to understand that it blows it out the back of the case is also something to do with your cooling, which we're going to talk about in this chapter as well. If the, and I probably have a picture later in the thing, but I'm going to go ahead and draw it here. If this is air going out here, this is my PC, this is the front of a traditional PC, and this is the back. Okay. That means that air is being pulled in through the front of your PC. It comes up through here. It goes out through there in a traditional PC. If I go and add a cooling fan, which many PCs have additional cooling fans, what direction should that be blowing? It's a 50-50 guess. You can say out or in. Out. It should be going out. What happens if I make it go in? Where is it pulling air from? It's pulling this nice hot air that just got blown out right back into my PC. And that's the last thing we want. Okay? So a good cooling fan should blow the same direction as the power supply. In other words, if I have the cooling fan here, it should be going this way. If I have a cooling fan in the front, which mine does at my computer, it should be sucking in because it should assist the flow of air through my PC. Okay? So if the hot's coming out the back and the cool's coming in the front, I stick with that plan. Okay? Hot going out the back, cool going in the front, so I'm going to suck that way. Mine has one here as well. Which way does that one go? And I'm going to tell you, I don't know which way to put it on best. I know what it does. Mine blows out on mine because that's the way it came on the case. Because the CPU is right underneath and it's just blowing it out. It's kind of sticking with it because it's coming in here, but I don't know whether that side case fan kind of messes with the feng shui of all the air going this way or not. But the point is, you don't want to suck hot air in that just got blown out right above it. Okay, you want to keep it blown out. That's also why you see a lot of dust and dirt inside stuff in the front of your PC. You look at a PC and these will be covered with dust. Your CD-ROM could have dust all inside it. This is not sealed. The air could come in through the CD-ROM just as easily as it come into the front of this case. And if you have it on the floor in your room and it's just pulling dust and dirt in from your floor, you can pull it right in and ruin your CD-ROM. Just so you know. Okay? That's why I like putting a fan down here to kind of force the air to come in here as opposed to just being sucked through my other devices, which it still can happen. Okay, so that's an important point, and that's why we talk about the way that the air flows through our PC. Okay? So, we've already said this. Our case, our power supply, and our motherboard have to match up. For our form factors, the power connectors that we have, and I just showed you this, we have this one's called the P1 connector. P1 connector, that's the big connector on here. And that says 24 pin. So this is a big P1 connector on my power supply. It can also be 20 pin. This just goes like this. If I to use 20, I can go like that, plug in 20. That's for older motherboards, so I can go like this and hook that on and put it for 20. And look, it even has a little direction. Look, it says 420, 424. You know how many times I've helped people and said, hey, you need to order a new power supply, and then they tell me I had to send the power supply back because it was too big for my computer. And all they had to do was slide the end off. You ever had anybody do that? Okay, and then there's a second power connector for the CPU somewhere on the motherboard, usually right around the CPU. It says 4 pin on this. It can be 4 or 8. Okay, depending on, you saw this on this motherboard. This is an 8 pin power connector right here. It means it has 8 holes or it could be a 4. Doesn't really matter. You have to have that plugged in order for it to work. If you buy a motherboard, if you buy a power supply that only has a 4-pin and you need an 8-pin, you just bought the wrong power supply. This one has both, so I can plug in either kind of motherboard to this one cable that runs over to where I put my motherboard plug-in. Okay, so I've got to have those, and I've got to make sure my power supply that I buy matches the motherboard that I'm buying as well. Now, I already said this, you guys aren't actually doing this project. I'm going to do an example project on power supplies, and really you guys won't purchase a power supply until the very last project. Okay, the very last project of the year, you guys are going to present a whole system that you purchased for X amount of money. It may or may not be the one that you've done research on throughout the year, because what we do is we spin a wheel, and Lane will get $500, and you'll get $1,000, and you'll get $1,500, and that's how much you have to build a PC. And if Lane bought all parts that cost $2,000 throughout the year, and he always showed us the most expensive, most awesome thing that he could find, and he ends up with $500, he's not going to be able to use any of those things. Okay, so that's the only time you're going to have to buy a power supply. But you have to remember these things, because if you buy a power supply and present it, I will be watching to see if the thing you presented, I bought this power supply and I bought this motherboard, will it work together? Okay, which is kind of the point of the very last project. Can you pick things out that work together? So we've got 2 power connectors on our motherboard that we have to match up. Okay, so the way the ATX form factor works is this is the base of ATX right here. Okay, the smallest ATX board starts with this layout, and then it grows to the side from there. Okay, so when it said the dimensions of ATX, that's a full-size ATX. There's also mini ATXs, they're micro ATX cases, but the base of the ATX board lines this stuff up right here, where we have our back panel, our CPU, and our memory in a row. Okay, so is that would be weird if that was no. It looks very similar though. So look how similar that is to the one I'm holding right here. This could be the same one, but it's even the same manufacturer. So I've got my back panel connectors, my CPU, and my memory in a line. And when it said they rearranged these to be out of the way, it means that now I've got all these extra connectors that no matter how big the board is, these things are not in the way. These are all on their own over here, and then I've got all these expansion slots that don't interfere with the CPU and stuff. Because if I had this CPU fan on top of here, and the I/O boards or the expansion slots were anywhere in line with that, would I be able to get something there? No. No. This is a really nice, big, huge cooling fan that I should not have taken off this board. I was trying to put it on something else, but I don't have the connector to do it. So anyway, so this is the main stuff. When I look at it, you guys need to be able to easily identify that this is where the CPU goes. This is what memory looks like. These are what the memory slots or banks, called slots or banks, slots or banks, called slots or banks. I said it way more than 3 times. That should be written down in your notes already, okay? So memory slots or banks look like that. You can have anywhere between 2 to, I think 8. It's about the biggest, okay? On some really impressive motherboards, 2 to 4 is normal. Okay, when you get up to 8, you've just got this mondo amount of memory slots. So I've got those. They're color-coded in this case. I've got my CPU socket right here. There's 2 different kinds of CPU sockets that I'm going to see, and I say 2. There's way more than 2, but there's 2 that when I look at them, they're visually different. Okay. And those 2 kinds of sockets we'll talk about more during motherboard, but I need to know that's where the CPU goes. And then I've got these back panel or input-output panel connectors, and those are all different depending on the kind of motherboard I have. Okay, that's part of the motherboard when I choose it, but it's basically, because it's ATX form factor, it fits to a certain size and shape here in the back, and then I get this back panel that goes in my case that matches up with this motherboard. That's not this one, is it? Where is this one? That is this one. Oh no, that just looks a lot like this one. Because that's a gigabyte one too, isn't it? So this is the one that goes with this one that would go on this case to make everything match up. It almost looks exactly the same, doesn't it? Huh? Me who? You didn't send that back. That was supposed to be
I
sent
just
back.
thought of that.
Hopefully they don't inspect that box too closely, since we forgot the back panel and the
And what?
SATA connectors.
But
But
that
that,
that big a deal.
that
That's
is
probably
that big of a deal. Who's? We made a new server in here and it wouldn't do it, so we sent back the CPU and the motherboard. Okay, so once we get past those base things, let's see if I can. Yeah. Woo. Then we have expansion stuff out here that expands on the basic connectivity of the motherboard. So I've got this input-output stuff here. That's the basic function that the motherboard has. That's on that input-output or back panel. And then I've got additional slots that add on to that capability of the motherboard. And this is where I get to, okay, what kind of ATX is it? Okay, so this is the diagram of how ATX is laid out. Okay. One second, it's a little off my slide. Let me see if I can. Okay, so when I say micro ATX, then it only has this part of the board with these screw holes. In fact, you can get one that's as small as just those 4 screw holes there. And then as you get bigger, it adds these screw holes, then it adds these screw holes here. So when I say it's a full-size ATX case, it means it has spots all the way out to here to screw in my motherboard, and standoffs work too, so it doesn't sit on the case. Okay, and a standoff is a little screw that holds the motherboard off the case. And you saw when we took apart those ones and put them back together, there was those little kind of nuts in the motherboard. That's a standoff that these sit on. And all those things have to align for the form factor to be right. Okay, so here's a bunch of different cases. You can see we go all the way out to a full-size ATX, and they all look very, very different. Okay. And that's why you have to pay attention when you guys are selecting that you have the right form factor, because the screw holes are different, everything's different, the power connector can be different, so you have to make sure the form factors match when you guys make your selections, okay? It's easy to fall into, that's cheap, this does what I want it, and then all of a sudden I've looked at so many that I've got the wrong form factor, okay? So not only does the form factor have to match the case and the power supply, you see the CPU sockets here are completely different. This one has one built in, as does that one and that one. So that one looks completely different than this one. My form factor or my socket set has to match between the CPU and the motherboard as well, which we're talking more about in Chapter 4. But there's a variety of different ones that you can see there, okay? And here's another diagram showing the different sizes and shapes of different form factor motherboards. And there's some different, these are all the same model of PC, okay, but they're totally different form factors. So if you're going to buy a replacement part for a 780, you have to know whether the 780 is a tower, a desktop, a small form factor, or an ultra small form factor 780, or you'd be getting the exact wrong part. Okay, so you could Google, I want a GX or an Optiplex 780 power supply. But you can tell this one and this one and this one are all different ones. So you have to make sure you've got the right form factor as well. And this is another picture of different form factors of power supplies that you have to make sure match. This is a standard ATX case power supply, and these are more specific for some specific case they go with. So you need to make sure you're getting those things that match up when you're picking out your power supply. Okay, we already said this. Describes the form, size, shape, and general makeup of a hardware component, and form factors of those things have to match. That's objective number 1 for today. And I'm going to stop right here. Questions? Anything match up with what you've read so far that you're like, okay, that make more sense, or no? Not yet. Not yet. Okay. Does everything make sense that we talked about? Do you everybody understand the definition of form factor? And the idea that ATX and BTX and ITX, these are all different ones. You have to pay attention when you're reading And you have to keep paying attention, because that's what I think happens. Lane goes and reads about 40 different motherboards, and then all of a sudden he's found this one that looks great, it's the right price, has the right stuff, and he's dropped out of his brain the whole fact that it had to be ATX. Okay, and I think that's why when people are doing these projects, all of a sudden they miss the one crucial thing that was the most important thing. They got all the other parts right and didn't get one that matched the form factor, and therefore it wouldn't go in their PC. Okay, so this, although it's the most important thing, it's also the biggest thing that gets dropped out, because later I'm going to be saying, okay, Lane, it's got to have 4 SATA slots, it's got to be an LGA 775, it's got to have integrated audio, it's got at least 7 channels. I'm going to give you all these other things, and you're going to drop this part out, that it had to be ATX. Okay, so nobody's got any questions? Okay, so now we're going to move on to electricity and electrical power. Okay, electricity and electrical power. Make sure we understand the basics of electrical power, because in order to do some of the stuff that we're going to do in this chapter, specifically on computing power supply voltages and wattages, we have to understand what those terms mean. I don't know if this is going to work anymore. Oh, I don't have any my sound up anyway. None of my animations work anymore with the new version of Smart. It makes me sad. But I'm still going to see if the sound. Let's see. Yeah, I guess the sound works at least. Bam. No? Yeah, of course it's AC/DC. Okay, so it's AC/DC. So we're going to talk about electrical power, and the answer is I had to cover that because you could see through it. Yeah, it was like I had it like this. I had it like this, but you could see it. It's supposed to be invisible. So I did that anyway. So we're going to talk about AC and DC power, which has nothing to do with the band, obviously. So what is AC and DC power? Okay. First, AC is alternating current. Okay. Alternating current is the most efficient method for transmission of electricity. It's what comes out of our wall outlet. Okay. That's what plugs are. That we get AC power, and the reason we get AC power is because there would be no way to transmit DC power all the way from Cincinnati or wherever our power comes from to National Trail, DC. AC has to be used to transmit electricity. Okay, so it's alternating current. It's the most efficient way to transmit electricity. It goes back and forth. Direct current, however, is the kind of electricity that's required for electronic devices. All of our electronic devices pretty much use DC power. So how do we get AC power from our wall outlet to DC power for our electronic devices? Okay. First of all, we have something that's called a rectifier. And a rectifier turns stuff from AC to DC. And my slide is too big, it slid down. Let me see if I can unlock this and move it up. I cannot. I just scroll it down. How about that? It's even easier. Okay. So a rectifier changes AC to DC, and a transformer changes the voltage from one voltage to another voltage. Okay. So this is one of those things that we plug into a wall to plug into our some electronic device. Is it a transformer or a rectifier? It's a trick question because it's both. Okay? This works as a transformer and a rectifier. It rectifies alternating to direct current, and then it transforms it to some lower voltage. Okay? And the only way to know the voltage is to read the power supply itself. Okay? So this one changes it to 12 volts out. This particular one changes it to 12 volts out. Okay? Now, just because, and this happens all the time, people ruin things all the time because they go and do this. This fits into the end, so therefore it goes with whatever it fits into. Okay? But every single one of these has the potential to change it to a different voltage. Okay, so you need to make sure whenever you plug in a power adapter that you're plugging in the right one to the right device. Okay? Because if you plug in the wrong one, you can easily burn it up. I've done that personally myself more than once because I thought I knew which one went with, and it just looked like it, but it wasn't the right one. Okay? So we've got alternating current that cycles back and forth. It's the most efficient method of transmission of electricity. I will ask you that question. What's the most efficient method of transmission of electricity? And you're going to say AC. Okay? And what do most electronic devices use? And that's DC, direct current. Okay, I guarantee you, I will ask you that question. There'll be a matching. There'll probably be a true-false. There'll probably also a multiple choice, because I don't ask the question, if you've noticed from the first test and the second test, I don't ask the same question once. I ask it a multitude number of ways, because I actually want to know if you know the information. If I do one matching that says AC is this, DC is this, and Lane gets it wrong, does that mean he doesn't know or he made a mistake? I don't know. But if I ask it 3 times and Lane gets it 2 out of 3 times wrong, then he probably doesn't know. Okay? So that's why I ask the same information in different ways on a test. So you'll notice that on my tests over and over again, that you'll see the same question asked. Sometimes I actually ask the same question. Actually, exact same question twice. That's not on purpose. That's an accident. Okay. So transformer or rectifiers change the AC to DC. Transformers lower the voltage. This is also a transformer rectifier. Okay. We get AC voltage coming in right here. That's 115 volts. Okay. And the biggest voltage that comes out on this side is 12. Between 3.3 and 12, we're going to learn which plug does which. Okay. But so it not only changes it to DC, it also lowers the voltage substantially, which is one of the reasons these get hot. That's why these get hot. When you plug in a device and you think this seems warm, it's because it's totally changing the power, and there is heat generated in that process. Okay, which is why the power supply is one of the warmest, not the warmest, but it's one of the warmest components in our PC, and that's why we want the air blowing right out the back, because all this heat we want going straight out of our computer. Okay, the other warmest one really is our CPU itself. Okay, the power supply will not cool itself other than that fan if it gets too hot. The CPUs are smart enough that they will get slower and slower and slower to try to cool themselves. This will just burn up if it gets too hot, and your PC will just stop working. Okay, so what does all that mean? Let me go back here. So AC power, and I may have another slide on this, but AC power, or alternating current, basically goes back and forth on a sine wave as it's transmitted, and this sine wave is at a specific speed, or 60 hertz. That's 60 hertz, and hertz is 1 cycle per second. Okay, hertz is one of the things you need. That's a 60. I'm going to rewrite it because it's so messy. Hertz is 1 cycle per second, and this sine wave, it goes through that sine wave 60 times a second, so it's going at 60 hertz. Okay, that's what our power cycles at. When we say alternating current, alternates, the sine wave alternates 60 times per second in US power. Okay, and ours is coming in also at 115 volts. And it cycles at 60 cycles per second. Cycles at 60 cycles per second. I said that at least 3 times. I'm stomping my feet too.
Wait,
Okay.
just repeat that one more time.
AC power in the United States cycles at 60 hertz or 60 cycles per second. That's the speed that it goes. Okay. And again, foot stomping is maybe it's an Air Force term. It means you will hear this question again. Okay, so if I'm up here and I'm saying something like this, and you see me going like this, I'm saying that fact should be written down in your notes. Okay, I don't have a foot that's fallen asleep, and I'm trying to wake it up. Which could happen. That would be really bad, wouldn't it? If I was going like this. What else do I write down? Okay, so that's AC. DC power is just meh, whatever the voltage is, the voltage. Okay, it's very flat. Okay, and again, AC, large distances, DC, short distances. And the C-141 that I used to fly, this one, this big behemoth right here, do you think everything worked on AC or DC? That right there is too big for DC power. We had 3-phase alternating current power, and then it was, you don't have to write that down. It's just interesting, good to know stuff. And even the 53, which is also pretty darn big, it's 50 feet long, too big for all DC. All the power in these aircraft systems were alternating current until it got down to right there at the instrument panel, and it was changed in direct current for whatever that instrument was right there. In fact, there are some instruments in the aircraft that just ran on 3-phase AC because they did so much power. Direct current power, DC, just has a voltage. And we're going to talk about what voltage is, but it's flat. Okay, it does not cycle at all, and that's why it's good for electrical components. Okay, so we need to know 3 of these terms really well. One of them I don't use in this class very much, but I'm going to go over what the term is anyways. Let me see, do I have it hidden underneath there? No, I just put it so that I could write on top. I couldn't remember. Okay. So the first thing we have is voltage. Okay. Every electrical component, when you plug it in, has some voltage. And I already said the voltage of the outlet there is 115. Okay. Voltage is potential. And I'm going to give you some can't remember what the word that I'm trying to say, some examples of how to think of this. That's not the word I'm thinking of. Let me give you some. It's like a synonym, but that's not what I'm working out either. Okay, so voltage is the potential of a circuit. Okay. The amperage is current. And I'm going to explain this better, but you need to know these things. Voltage is potential. Amperage is current. Okay? This is how much can go, this is how fast it's going, kind of, when it comes to electricity. Okay? This is how much can go through it, and this is how fast it's going through it. What's actually going, wattage is equal to power, which equals volts times amps. Okay? So when I want to know how much power, it's how much wattage is there. And that's found by saying the potential electricity multiplied by the current of that electricity equals the total amount of power that we have. Okay? And this wattage is what we're going to be talking about a lot when it comes to power supplies. Okay? So every power supply has a specific wattage. Okay? Guess what that one is? 3 seconds is up. Guess what that one is? Okay, guess what that one is? What do you think the symbol of wattage is, first of all? Give it a guess. Give it a guess. What would
W.
W, okay. Give it another 3 seconds.
336.
Okay, give it another try. Okay, see, it says 500 W. 500 W ATX. 500 W. Okay, this is a 500 watt ATX power supply. It's the big bold letters. Okay, they're not trying to hide it from you, just so you know. Okay, so this one in particular can do 500 watts. That means that's a max that can come out of these wires to power your PC. And we're going to have to learn how to calculate what a PC actually needs. Because in the case of this one, the PC required more than 500 and kept shutting devices off. It couldn't power everything at the same time. No. You're going to be doing some basic math. It's really easy. Okay? It's like making a shopping list. Okay? Speaking of ohm, let's talk about the last thing of electricity. Ohms is resistance. Oops. Resistance in a circuit, and I'll be honest, we don't use that for anything. Okay? If you were an electrical engineer, you would definitely learn a lot about ohms, because when you do circuit calculations, you have to know what's going through it and how much resistance is coming from it. Yeah? Did my phone just ring?
Yeah.
I'm sorry, who is this? You're interrupting my lecture for a really important quick question. You're not interrupting my class for Katie's question where she's at. I'll call you when my period is over. Hi. She doesn't even work here anymore. It's for Katie Messer. Okay, so anyways, the ones that I'm going to ask you questions on are volts, amps, and watts. Ohms is the other electrical term, and it refers to the resistance in a circuit, and we're not going to be overly concerned with that. Okay, so here's the book definition. Okay, so voltage is the potential difference in a circuit. Okay, and we have different voltages coming out of our power supply. Amperages is the current going through those circuits, and I have a little example, kind of understand electricity a little more. And wattage is the total power calculated by multiplying volts times amps. Okay, and when we talk about power supplies, we really need to understand wattage to make sure that we're getting the correct one. Let's see if I have a little thing for my analogy. Nope. Here's where I just add the slide. Okay, so here's my analogy. That's the word I was looking for that was escaping my brain. Okay, so I'm going to use water as our analogy for understanding electricity. Okay, so if this is a garden hose, again, I think I've said before, I am not an artist. We'll pretend that's the same diameter the entire distance of that hose, and it doesn't get shrunk right there in the middle. Okay, so this is a water hose. Okay, the diameter of this hose would be the voltage. Okay, the diameter of the hose would be the voltage, because that's the potential water that could go, that helps define the potential water that could go through it. Okay, so the diameter or the size of the hose, if my hose is this big and it's a big water pipe, okay, versus this little tiny water pipe, look, I'm getting so much better with my drawing there, okay, the voltage is the difference in the size of the hose that defines the potential for water to go through this pipe. Okay, so voltage is potential. When we talk about potential, that's what we're talking. That's the potential. If I say it's a 5-volt circuit, it can only allow that potential amount of electricity to go through. Okay, so the size of the tube is an analogy for what potential or voltage is in a circuit. Okay, now when I turn on this spigot, and oh, my drawing just got a little worse. Let's say this goes out and down. There's my spigot, and I have to change my drawing a little bit. There we go. The amount I open the spigot is what? The current is the amperage. So, you know, when you turn on the water, when you go to a sink, you don't have to put it on full blast all the time, right? You turn it a little bit, you turn it a lot. You have a little difference, right? So the current equals amperage. That's how much is flowing through that pipe, okay? So the current is how much is being pushed through there, okay? That's the rate that it's being pushed through there, okay? That's my analogy there, okay? So current is how it's being pushed through. That's our amperage. And then down here at the end is our bucket of water, like my analogy, okay? So the type of pipe multiplied by how big we open it determines how much water comes out. I'm trying to make this stick in your brain, okay? So the amount that comes out is the volts times the amp, or the size of the pipe multiplied by how big we open the spigot, okay? That's how much total power we end up with. So wattage equals the potential times the current, or in my analogy, the amount we open the spigot by the size of the hose defines how much water comes out the end. Okay? Does that help you understand it a little bit? A little bit better? I like this analogy because I think most people have turned on a hose before. Okay? And you know that the more you turn on the hose, the more water comes out the end. If you had a big, huge fire hydrant, you get a lot more water. Okay? And you get a lot more water because there's more current and there's a bigger pipe. Okay? It's not because the water is any different. You just get a lot more coming out. Now, if you've ever heard this before, it's not the volts that kill you, it's the amperage. Okay? If I go and touch something and I discharge static electricity into Mr. Anderson here, I could discharge as many as 2,999 volts without even knowing I discharged static electricity into him, because there's no amperage associated with it. However, if I put 1 amp behind 2,999 volts, I would kill him. He would be charcoal. Just fall over and I go, ha ha, I am Mr. Electro, okay? So it's not the potential that causes the damage, it's the current behind the potential. Which is why when we go and grab a power supply like this, it's not just the voltage we need to look at. Okay, I look at this one and it says output is 12 volts, 1 amp. Can you read that on there? See where it says output? 12V, 1A. Okay, if I grab the wrong one, where are the other ones at? Okay, here we are. Okay, here is a box of those 1 gig switches. Okay. This is a 8-port 1 gig switch. And it says absolutely nothing on it. I can't find it on the bottom. So right there, okay. So it says power input. What's the power input of that?
5 volts.
Okay, what's the total power then? 5 volt, 1 amp. How many watts are coming in? 5. There we go. Woohoo! Look what we just learned. Okay, and then I don't have one in here. The 5-port one, the exact same manufacturer, okay, is 7.5 volts. 1 amp. Total wattage is 7.5. Okay, how much more is 7.5 than 5? What? Okay, how much? Let's talk in percentages. How much percentage more? Because 2.5 doesn't sound like that much. It's only 2.5 more. Well, let's talk about percentages. How much percent more is there? 33. Right, 33% more power. Okay, that's a lot more power, right? I think that's right, math. I'm doing it in my head. But 5 to 7.5, 25, 33% more. That's a lot more. Okay, if I plug the one from the 5-port one in to that 8-port, I burn it up like that. It's too much extra power coming in the circuitry. It's made to run on 5 watts of power, and you just put 7.5 in, and it goes, it's dead, never to return. Okay, so we have to make sure that we know what the wattage of the device is, or read the volts and the amps, and it's the right thing before we plug it in. Okay, so whenever I'm not talking about just here at school, I'm talking about at home too. You see somebody pick up something and just go plug it in, make sure they know that it's the right one. I don't know this. I should read it as well. But let's talk about the iPhone versus the iPad. Anybody have those two devices? Okay. Is it the exact same plug? Okay, so it's the exact same plug for the same generation of iPad and iPhone. It's the exact same plug. Okay, but an iPad power supply puts out 2 amps, and an iPhone puts out 1 amp. If you plug the iPhone into an iPad charger, does it hurt it? I don't know. It still works. It charges it, even though it's twice the amperage. Okay, but does it hurt the iPhone in the long run? I don't know, because it's very possible that it's damaging the battery, and your battery life, even though you charge it faster, could be less. I don't know. I right? But that's an example of things that match perfectly, but the little brick for the iPhone is only a 1 amp brick, and the one for the iPad, the big one, is a 2 amp. Same voltage coming out of both. Okay. Okay, I think we're done with the basic understanding of electricity. Good. There we go. Questions? Do we understand the basics of volts, amps, and watts? Okay. Let me give you a question. Okay. I'm going to ask you this on a test. This is plugged into a CD-ROM. It is. Okay, it's plugged into a CD-ROM. This is a 12-volt plug. By the way, if you don't know, almost all of them are 12 volts, unless I tell you otherwise. Okay, so all these are 12 volts, but this one right here is 3.3. Okay, the one to the motherboard is actually the least. It's the most amperage, it's the lowest voltage. Okay, so I plugged this 12-volt one into a CD-ROM. The CD-ROM pulls 2 amps of power. How many watts does the CD-ROM use? Right, easy math, right? Easy math. All you have to do is know, you have to know, I'm not going to tell you this is 12 on the test. Will not tell you this is 12 on the test. Will not. So if you didn't write down, all powers are 12 volts other than the motherboard, which is 3.3, you might want that in your notes. We're going to go over it again, but it's a good thing to have in your notes. Okay? So if I say it's got a CD-ROM with 2 amps, and I say how many watts does it use, you should be able to do that. 2 times 12. That was easy. Of course, it's easy because I'm telling you all the numbers right now, right? You can do 2 times 12. All of us got that math down back in second. Let's play 4th grade. That may be 4th grade. Is it 3rd grade math? Okay, third or 4th grade we did multiplication. Okay, so we know that volts times amps equals watts. This is the important number. We need to know the total wattage that a PC uses. These, you know one of these already. You always know the voltage because that's the potential of the plug. This plug has a certain potential, and then the device will pull some amount of power when it comes to inside a computer. Okay, so potential, current, total. Potential, current, total. You got that, kind of? Okay. So, there's other electricity that we do talk about, okay? And that's static electricity. I'm going to leave that up there for a second. I'm not going to read that whole thing to you. How many we got done?
4.
And are you programming them for the library, or
For
you just...
213?
Yes.
Yes. I'm turning the right floater back on.
Okay, so they're just ready to put in place.
I assume that's what you want to say.
Yes, that's exactly. Well, if they can do that whole center area,
How many do you need for that?
is it 12 and 4 or is it 8 and 4 for total 12?
No idea. I brought up 6. So we're going to get another 6.
I know that it's at least 12 that we need. I want
It might be
to
more than 12.
I want to replace at least 8 to be able to do the next row and then the class after this one.
But no, we're doing the next block, not third block.
The 4th block, we're going to do 8 in the library and move them to a Studebaker. Then on
Oh, you mean, okay, next Thursday.
Thursday, we'll do Studebaker's next row.
Is the font a different voltage?
What?
The font is different voltage. It's not. Nobody uses the font.
Oh, but in general, right. Okay. You guys understand what static electricity is just for reading that? It's that buildup of difference that I get when I walk around on my shag carpet and shock my sister over and over and over again until she screams. Never did that. Okay, I did. Sister's 3 years younger than me. I was mean. I was a mean big brother. I love my sister. I picked on her. And when she started screaming if I came into the room, she saw me going like this coming into the room. She'd just scream before I even got to her. I didn't do anything! Yes, he did. He shocked me. She was a liar. That's right. I probably taught her to be a liar because I did that. Okay. So just like we can shock our little sisters, we can shock electrical components, and we can ruin them quite easily. Static electricity ruins more components than people ever even realize. It may have ruined this. I don't know. It's hard to say if it did or not. So these are numbers you need to know. I'm going to give you. So in order to even feel the charge, when I go up and rub the shag carpet, touch Lane on the earlobe, see if it hurts more right there. That was an experiment. Where will Tracy scream the loudest if I shock her? I know, terrible. 3,000. 3,000 volts to even feel static electricity. Why is that important to you? That means that if you discharge 2,999 volts into a motherboard, you won't even know it. Which is why when we're working on computers, we always act like we have a static charge and we ground ourselves to things before we touch components. That's why when students just start coming in and grabbing stuff, I'm like, ah! Okay? Because they can easily ground themselves to that component by discharging into something that's fragile. Which is why we always touch the metal case, we always touch the power supply before we touch anything else inside a computer. Okay? A lot of computers don't have metal cases, that one does. A lot of them have plastic cases. Okay? You can't ground yourself on plastic. So you have to actually touch the metal part of the power supply. Why do we touch the power supply first? Because it's used to getting all kinds of discharge voltage from the wall. This is a hardy component. Okay? It's the hardiest component, but it's also the one that will usually fail first. Okay? But it's not going to fail from our static electric charge. So we always ground ourselves to the power supply first because we might have this in us. Okay? To hear that crack when you touch your little sister Tracy, it's 6,000. 6,000 volt to hear the little snap when you do it. And that's what you were shooting for. You were shooting for the snap. Okay? To see it, to see the crack, takes 8,000. Okay? And that's in the dark when she's asleep and she doesn't even know. She's like, that's just fun to see that little crack, have that wake her up. Turns out you can't get that when you're camping. I tried when we were camping. There's just no way you can do this as much as I want to on top of the sleeping bag, and I couldn't build up a charge. It just didn't work. Okay, so up to 2,999 without even knowing the discharge. When you hit the 3,000, you'll feel it. 6,000, you'll obviously hear it and feel it. And at 8,000, you'll actually see the light of the static electricity. If that happens inside your PC, you have probably done egregious harm to your PC. Okay. If you're working on your PC, you want to do it in a non-carpeted area, if at all possible, on a nice wooden surface, if at all possible, not a metal table. That would be a bad choice of things to do it on. If you've got a metal desk at home, it's probably not the spot to be working on your computer. So I guarantee you'll see these numbers again. And the real reason it's important is so you understand that. And if you ever see or hear it when you touch your computer, you know that you may have done harm to your computer. Okay? So we have some things that we can help control static electricity when working on computers. None of these things do we use inside at National Trail. Okay, but you can have a grounding bracelet. It's a bracelet that goes on, usually Velcros on your hand. It has a wire and an alligator clip, and you clip it onto the metal part of the case. You can have grounding mats. We have a grounding mat under the announcement system downstairs in the office. It used to have problems all the time, and I bought a really nice $40 grounding mat to ground it so it would stop shocking people when they picked it up. And now it hasn't had a problem for a really long time. When you buy electrical components, they come in these plastic bags. This is an anti-static bag, and that's so it doesn't, nothing gets discharged into it or from it. I'm not sure the purpose of putting a battery in an anti-static bag, but certainly video cards and CPUs and all kinds of other things come in static shielding bags so that they're not discharged when they're en route in between places. This is what we do. When we work on a computer, we make sure it's unplugged. We hold down the power button for 20 seconds to discharge any power that's built up inside the PC, and we make sure we touch the metal case or the power supply before we touch any component inside the PC. And that includes if you walked around the room and you came back to work on it again. I'll be sitting here working on a computer going like this. You'll see me, if I'm not touching something, I'm touching the power supply. Put my hands in there and I'm touching the power supply. I have not fried anything from static electricity in years. Did I when I first started working on stuff? You betcha. Okay? My training from college was as a programmer. I had this many hardware classes by programming. 0. And then when I was in Hurlburt Field in charge of 53s, I got put in charge of the computers for the squadron. And unfortunately, the whole building was carpeted and was my computer repair station that we had. I had 6 people working with me in that office, and we had a nice, not only was all the flooring carpeted, the workstation was this nice metal rack that was mounted on the floor, sitting on the carpeting. And that's where we repaired stuff. And I will tell you that when I first started, I didn't know any of this stuff. I never had any class. They just said, you're in charge of computers because you have a computer degree. I'm like, I have a software degree. I don't have a hardware degree. They're totally different things. But that didn't matter. I was the only one with a software degree, and it said computers. Actually, it didn't even say computers. This system's an analyst, but whatever. Anyway, so when I first started, I fried a bunch of stuff. I know there's stuff that probably would have worked fine if I would have taken some of these precautions. But I didn't know. And I will tell you that more than once I saw the spark. And I walk around the building and go, I gotta work on that. And I go up to it, and I go to reach in and touch something, and I'd see a little spark, and I didn't understand. Okay? Because I had no training or no degree in it. And so what did I do? After I fried a few motherboards, I got a book. I started reading on computer repairs, not just trying it willy-nilly, and I realized that we had a really, really bad setup. And in the terms of bad, you couldn't have designed a worse setup than where we were repairing PCs. Now, there's nowhere else to go. We had no non-carpeted area, but we ended up getting grounding straps, and I learned to grab the power supply. And after my first year of frying many things, I didn't fry anything again. Okay, so enough said on that. So you want to, and you're not protecting yourself, right? I mean, not that we want to get shocked, but when it comes to static electricity, you're not going to get shocked to death with static electricity, but you can certainly ruin a computer component, okay? So, continue our discussion about electricity in general. When we plug in, there's 3 different things that get plugged in a good outlet, okay? We have a hot one, which is the little one if you're wired right. The little hole is the hot hole if you're wired right. If your dad did your electricity or hired your Uncle Tom to do the electricity, or Uncle Bob, or whoever, or didn't hire him at all and gave him a dinner for helping him with this electrical work in a shop, it may or may not be wired correctly. That's supposed to be the one that hurts right there, the little one. Theoretically, you could stick a wire in that one and it wouldn't hurt you at all. Theoretically, don't do it. Okay? The big one is neutral, and the other one on the bottom is the ground. It's not hooked up to anything electrical at all, if it's done correctly. The ground goes to your circuit breaker panel and then goes to the ground. That's why it's called ground. Okay? It goes to a big steel rod sticking down into the ground 5 or 10 feet. In an old house, they used to just hook the ground up to the water pipes. Tons of my water pipes are not metal anymore, they're plastic. Okay? So, and that, by the way, is not approved on new construction. You can't hook it up to your water pipes like you used to be able to, because there's too many places that coming into my house, it's not metal anymore. But I grew up on old houses, and here's our water pipe, and there was this big clamp, and the wire went straight to it from the fuse box. And that seemed okay then, because everything was this big, huge iron pipe that went into the ground and went out to the road. And that iron pipe was down on the ground for a substantial length of space before it turned into some other kind of pipe, and it was extremely well grounded. I have no metal pipe going out of my house anymore. Okay? Because the contractor, when he did our addition, had to move our plumbing. There is a 1-foot section of, I don't know, I'll say plastic pipe, where my iron pipe comes to here, goes into the ground, and then I've got this one piece of plastic, and then it comes in to PVC actually after that. So if my house was grounded to my plumbing, nothing is grounded at all. Okay? And frequently, what happens is, that's how your ground works. Then the plumbing changes, and nobody goes back to check that. Okay? If you have a plumber in your house, the last thing he's worried about is your electricity. That's not his job. Okay? So if you have a plumber redo your piping, and that ground is going to the piping, and he redoes it in the new PVC or plastic, your whole house is ungrounded at this point. If you're in an old house, it's an important thing. Because this ground is the most important thing when it comes to plugging in electrical stuff for us. Okay? Because without a good ground, no surge protector works, no backup power supply works correctly. Okay? So you have to have grounded outlets for that to happen. And in my church, half the outlets aren't grounded at all. They're 2-prong outlets. And if you see just a 2-prong outlet like that, it's old. Okay? There are sections of my house that are still knob and tube with no ground at all, and no electrical stuff gets plugged into those outlets. That's important. My light bulb, the floor lamp, doesn't matter. Okay? But if it comes to my stereo and I plug into that, I am hoping that my stereo lasts for a while. Okay? So I've got hot, neutral, and ground. The way electricity works is it comes in through here, goes to my component. This is the light bulb. And then it goes back out. And the way this flows through there is what lights up this bulb. And the rate that the current goes through there is what determines how much electricity this uses. Okay? Because it's the movement of that power that causes that filament to light, or that air conditioner to cycle or whatever. Okay? So, got hot, neutral, ground. Don't ever trust those. If you ever work on electricity, every book you ever read will say turn off the breaker. Don't play with it, because you never know. Maybe this is black and this is white, which is what it's supposed to be. Okay? But maybe it's cross-wired down at the circuit breaker panel. Unless you did it personally, how do you know? Okay? So you have to be very careful with that and turn the breaker off. When we do, I'm going to get back to this. I didn't realize we're still on electricity. When we do this in this grounding strap, really this is not an electrical plug. There's no, the other hot and the return aren't there. That's just a grounding strap. So you're plugging into your ground wire. So it's like a wire that goes straight into there that grounds you to the world. Okay? To the earth is what this ground is. So this is plugged in with a wire. So the computer is plugged in with a wire that has no, it doesn't have these prongs right here. It just has that to ground your computer. Okay, so if you're like, why would he have it plugged in? That's why. And then he's got his grounding strap hooked on with an alligator clip to the metal case. You can also have grounding mats, which is what we've got downstairs, and then we've got the anti-static bags, which I already showed you. Okay. We're going to get back to the power, I think, because I want to talk more about that, but I think we talk about it with UPSs and power surge protectors. Okay, so I've got a power supply, and I've got some other pictures on here, but I've got my power coming in, and if I look in the back of here, these are made, this one is not, these are made to work in various environments. Let's see if I can find one. Not falling. By the way, fire inspector is coming tomorrow. We need to make sure there's no cardboard up on the top of this stuff. We need to move those off. And I'm very worried about the closet in the hall, but I've warned them. He's going to throw a fit when he sees all that crap out there. That's not us. Sorry, got off track. Pass. So this has a little switch right there that says 115, and then the switch. You switch the switch. This now says 230. Okay, so this can be plugged in Europe right now. This computer will work, and now it's plugged into the United States, and this computer will work. Okay, it's just telling you what is the input voltage going to be. That's why it says 115, 230. That's a switching power supply that you can use. I'm not even going to tell your story. Switching power supply that you can use in either location. This one doesn't have that. Yeah, it does. It's over here. That's weird. I've never seen it not. Have you ever seen that? That's kind of cool. It's on the inside. I really like that, but it's not here on the outside. And the reason I like that is because you know where you're going to be when you build the computer. We used to have in Lab 210 lovely students who would switch this all the time when they left. Fall out. Or they just reach back and switch it. And then the next student who came in, the computer would run for like 2-3 minutes and shut it because it wasn't getting the right voltage and the power supply would just turn itself off. So I like the fact that this one's on the inside so that if you have it switched right, nobody else can change it. Of course, that means you have to open your PC when you move to Europe, but how many people can open to Europe? Anyway, so we've got different plugs down here. We're going to talk about the different plugs and the different voltages of the different plugs. I don't like that picture. Let me go to a different picture. And I'm going to have to pick a different picture from my gallery. Where is... There we go. Chapter 3. Let's see if I can find a better picture that I like better. I don't like any of those pictures. I'm going to add a new picture for myself here. Yeah, I don't need any eggs this week.
Okay. That's probably good because I'm like down in production.
I know you said that, so
Maybe thinning of the herd
I have a friend who said that
and the
if you
filling of the fridge.
that if you got a timed light in your thing,
Yeah,
you already do that. Okay.
Yeah, except mine's not timed. It's on all the time.
That's not. It's supposed to be timed to let them know when morning and night is. It's just not all the time daytime. How's it working for you?
It works good.
It does not. You just said you had lower. There we go.
Did you not hear? I just put it in like 4 or 5 days ago.
Oh no, I didn't.
So it takes a little while for the little bodies to get acclimated.
Okay, so I like this picture. We use this picture instead. So here's the end plugs of a bunch of different plugs that you can have on your power supply. Okay, so is he heckling? What's he doing in here? Go away, Mr. Wassam. Go away. Lock in place. There we go. Okay, now I can draw it. Okay, so these are a bunch of different connectors. Now, every single one that you ever buy is going to have a P1 connector. I'm going to use green now. This is the P1 connector right here. Okay, it's either 24 pin or 20 pin, or it's a 2024 pin. This is a 2024 pin. Okay, because it can do either. This one is same thing, 2024 pin. The The Dell ones are just 24 pin. They're not made to go back to 20 pin. And in general, I don't even know if they make any motherboards that take 20 pins anymore. They're older motherboards, okay? So this is 3.3 volts. It's 3.3 volts, okay? Your P1 connector is 3.3 volts. Okay, just making sure. And I said everything else is a 12 volt, and I lied. The floppy drive one is 5 volts. Everything else is 12, 12, 12, 12, 12, 12. Okay? So if you're in doubt what the voltage is, it's 12, except for the floppy drive is a 5 volt connector. Okay? How many floppy disk drives? That's what the FDD stands for. How many of those do we have anymore? Not many, right? We're not going to connect many of those up. They can go to other auxiliary power things as well, but in general, they're all 12 volt connectors. Okay, the P4 is a 12 volt. This P6 is a 12 volt. The PCI Express is a 12 volt. SATA connectors are 12 volts. Okay, they all go to something inside your PC. Now this one is a motherboard connector. This one is a motherboard connector. And I don't have the other one. That's the only motherboard connectors on that one. There you saw from the one, there's also an 8-pin P4 connector for your motherboard as well. Okay. The P4 stood for Pentium 4, but they're all more than Pentium 4s anymore. But so we've got a P4 connector that goes to your motherboard. They can either be 4 or 8 pins. Okay. Those are 12. And then we've got all these other ones that are 12 as well. And I guess because the bell has rung, we'll call that a day for today. And I will see you guys on Thursday.